Uh, so um, the first assignment was due, first written assignment, excuse me, was due last night. Um, so I have that graded for you today. And we've got these next assignments coming up. So Wednesday, Thursday, Monday. Okay, P4, 5, and 6. All right, a couple problems from each section. Again, you need to be doing a little more than that. Not. You need to be doing the discussion problems. I mean, it's not really enough practice, just those. But I do want to get you the feedback you need. With some assignments. So that's why we're doing these written assignments. Web assign, first one due on Wednesday. The next one will be due on Monday. Exam 1, it's going to be covering sections P2 to P8 and sections 1.1 to 1.4. So we're not too close to finishing covering those yet. So I can't announce, I can't, say exactly when the first exam is going to be. Maybe Monday of, maybe Monday the 31st. Seems about the right time. Okay, but I'm not sure yet. I'll announce the date of the exam at least 1 week ahead of time. Okay, so in the next few days we should have an idea when it's going to be. So maybe the 27th, maybe the 31st. All right, so I want to work on problems from section P5. There was one more thing in P5 that we didn't quite cover yesterday that I want to do. So it was just in the last couple minutes. We weren't able to get to that, but let me mention it to you. And it's a common mistake, so I want to clear it up right away. So we were talking about multiplying rational expressions or polynomial expressions, more often polynomial expressions. But when you've got two the colorful one, there it is. When you've got two polynomial expressions or algebraic expressions, so remember those are sums of monomials. A monomial has just some power of x multiplied by a real number, and then you add so many things together to get a polynomial. So monomial, polynomial. So you get 3 terms in one polynomial, 2 terms in another polynomial, and you want to multiply them together. You multiply each term in the first by each term in the second, right? 3 terms here, 2 terms there. 3 times 2 is 6. So you're going to get 6 terms. 1, 2, 3, 4, 5, 6. All right, so 3 terms here, 2 terms here. 3 times 2 is 6. 1, 2, 3, 4, 5, 6. And then you simplify the expression by adding together the like powers of x. The mnemonic that is taught in high school, FOIL, first, outside, inside, last, I'm not sure why that's, been saying FOIL since before I was born, and they were saying it while I was in school, and I'm not sure why it's still around. But when you have a polynomial with 2 terms, and 2 terms here and 2 terms there, then you multiply together the first terms, the inside terms, the outside terms, and the last terms, like that. So you get 4. But it's just every term in here by every term in here. So, and then, we had this example as well. 1 term, 3 terms. So you just multiply the 1 term by every term here. So that's just distribution. Now the final thing, so powers of polynomials and algebraic expressions. remember, okay, ab to the n is equal to a to the n, b to the n, and a over b to the n is equal to a to the n over b to the n. Do not, okay, however, do not think, however, well, not do not, but it is not a plus b to the n is not a to the n plus b to the n, okay? Exponentiation distributes over multiplication and division. Exponentiation, which also is square roots, because square roots are rational exponents, cube roots, fourth roots, all that good stuff. Okay, exponentiation distributes over multiplication and division because it's defined in terms of multiplication and division. Exponentiation, because it's defined in terms of those things, it ends up behaving nicely with respect to those things. Okay, but it's not defined in terms of addition, exponentiation, and it's no surprise that this is not the case. All right, a plus b squared is equal to, well, it's a plus b times a plus b, right? A plus b times a plus b, which is equal to, well, multiply every term in this by every term in this. So first terms, to use the FOIL, a squared. Inside terms, or outside terms, a times b plus b times a plus b times b. Let's write it out like that. Why not? A times a plus b times a plus a times b plus b times b. All right, this is a squared. This is, remember, multiplication is commutative, so I'm just going to write that as ab plus b squared. So this is equal to a squared plus two of these plus b squared. All right. So a plus b squared is a squared plus 2ab plus b squared. It's a plus b times a plus b. So it's actually fairly complicated. It's actually fairly complicated to evaluate a plus b to the n. I mean, just for a plus b squared, it's already a little bit of a mess. A plus b to the third, right? Well, that's a plus b times a plus b times a plus b. Right? Well, a plus b times a plus b was this. Right? These two, a plus b times a plus b, was that. And now you have to do it again. Two terms in this polynomial, two terms in that polynomial. So this is a times a squared is a to the third. So I'll write out the whole thing. So a squared plus a to ab plus ab squared plus ba squared plus b to ab plus bb squared. What's a squared? What is this? How does that simplify?
A to the third.
A to the third. This one, a to ab. So we have a and a, so that's a squared. All right, customary to put the number out front. 2a squared b, ab squared. We'll write this one as a squared b plus, this one is 2ab squared plus b to the third. So we've got 2a squared b plus a squared b. So how many a squared b's is that? How many of these two red things?
3.
3 of those. And 3 of the blue things. Alright, so we've got a to the third plus 3a squared b plus 3ab squared plus b to the third. So it's not a plus b to the third is not a to the third plus b to the third. It's complicated. There's shortcuts to doing it, but I mean, the shortcuts to doing it just, basically make sense of the complexity. Okay, so let's not make that mistake. All right, people do it all the time, so let's not make that mistake. So exponentiation behaves nicely with respect to multiplication and division because it's defined in terms of multiplication and division. Exponentiation does not behave nicely with respect to addition because it's not defined in terms of addition. Right? It's a very kind of simple way of looking at it. All right, let's do a few problems in P5. So 15 to 75, every sixth problem. And which ones did I assign hand in? 70 and 78. Let me circle those so I can do stuff like them. 70 or 78. Okay. All right, let's try 15 to 75 every sixth problem. Oh, okay, so 15, are those divided by 6? 70, no. No. So 15, let's see, 21, 27. Let's look at 27. So 27 we have 2 times 2 minus 5t plus t times t plus 10. And they're asking us to simplify the expression. Okay? Simplify the expression or expand. All right, put it in standard form. Standard form, they don't say what it is in the book, but what I mean by it is, and what pretty much everyone else does would be, is to write it as a sum of monomials. Okay, so this right now is not a sum of monomials. Okay, so in order to do that, first let's multiply the 2 with the 2 minus 5t. So 2 times 2 is 4, minus 2 times 5t is 10t. Plus, now let's multiply the t through here. T times t is t squared, plus t times 10 is 10t. All right, so now let's add the corresponding powers of t. Starting with the highest power of t, I have t squared. And then I have plus 10t minus 10t. Gives me how many t's? Plus 10t minus 10t. How many t's does that give me?
0.
0, so we just leave them out. And then I got the 4t to the 0. Right, so the term that in a monomial, the term in a polynomial that has no power of t is actually like t to the 0. So t plus 4. So every sixth problem. So 27, so 33. Let's try another one of those. Let's say like 29. It's not one that's assigned, but similar to it. So let's take a look at it. R times R squared minus 9 plus 3R squared 2R minus 1. Okay, put it in standard form. So a sum of monomials. So in order to do that, let's multiply the r through here. So r times r squared is r to the third, minus r times 9 is 9r. 3r squared times 2r. Let me just write it in a couple steps. And then 3r squared times minus 1 is just minus 3r squared. So what's this term? Okay, how do we multiply these two monomials together?
6R to the third.
Right. You multiply the real number coefficients together, it's 6, and then you multiply the expressions for r, the powers of r. R squared times r is r to the 3. You add the exponents. So 6r to the 3 minus 3r squared. Collect the powers of r, the terms with the same power of r. So I have 6r to the third and 1r to the third gives me 7r to the third. R squared, I just have the 3. And then the 9r. And that's everything. Alright. 33. 39. It's a sixth problem. Did I start the recording? I did, yeah. 39. So 3x plus 5, 2x minus 1, put in standard form. Alright, so, we have a polynomial times a polynomial. 2 terms times 2 terms. So we, use that FOIL idea, or just multiply every term in the first by every term in the second. So 3x times 2x, let me write it out a little bit more fully this time. Not because I want you to do it, but just in case you're not quite seeing it yet. Just like that. So I have the 3x times the 2x, the 3x times the negative 1, the 5 times the 2x, and the 5 times the negative 1. So every term in the first by every term in the second. Simplify the monomials. So this is 6x squared. This is minus 3x. This is plus 10x. This is minus 5. And then I have 10x minus 3x, which is 7x altogether. Okay. So it's 39, 45. 45, we've got one of these exponents. So 5x plus 1 squared. Again, put it in standard form. So a sum of monomials, where the power of x in each monomial is different. This is a sum of monomials, right? But the power of x is the same in these two terms. So we really should combine them. So here we've got 5x plus 1 quantity squared. So that is 5x plus 1 times 5x plus 1, right, which is equal to, by the way, note the way I'm writing things, we're evaluating an expression. There is no equation on the page here at all. Okay, this here is an expression. It's not an equation. This here is an expression. What I'm saying is that this expression is equal to that expression. And this expression is equal to that expression. This expression is equal to that one. And that's a suitable answer to the question. Okay, we are writing a string of equalities to evaluate an expression, the way I like to say it. A string of equalities to evaluate an expression. There's no equations on the page yet. Okay, an equation is, a right-hand expression and a left-hand expression equal to each other, and you want to quote-unquote solve that equation somehow. Equations are things you solve, typically. Sometimes you do other things with them, but typically they're things you solve. Okay, we haven't done that yet. We will, but we haven't done it yet. We're just working with expressions. All right. So first, outside, inside, last, or every term in here by every term in here. 5x times 5x, 25x squared. 5x times 1 is just 5x. 1 times 5x is just 5x. Of course, these two are going to be the same. And then 1 times 1 is 1. So I have 25x squared plus 10x plus 1. Okay, these will be important later, by the way, these squares of polynomials. So it's 45, every sixth problem, so 51. 51, another squaring thing. This is a polynomial that has two variables in it, which is fine. Sometimes you can have such things. If your mathematical education takes you to Calc 3, you'll go on to multivariable calculus, in which case you deal with expressions having two variables or three variables or even four. And so, here, not so much, or if you take physics or chemistry, you'll have plenty of those. So it's a two-variable polynomial, which is fine. You just treat the variables as variables, and the way we've been doing them. So this is 2x plus 3y quantity squared, times 2x plus 3y. So 2x times 2x, 4x squared, 2x times 3y, 6xy. Of course, you can't combine the x and the y. Plus 3y times 2x is again just 6xy. 3y times 3y, 9y squared. And of course, these two in the middle, right, they have like powers of x and y. X to the first times y to the first. X to the first times y to the first. So that's 12xy. Okay, so same idea. You collect together monomials. So a monomial of two variables has got a real number, a power of x, and a power of y. Well, the first variable and the second variable. So here, this is 4x squared, y to the 0. 12x to the 1, y to the 1. 9y squared, x to the 0. So you can combine monomials that have the same powers of each variable. Every sixth problem, so that was 51. So 51 minus, let's say 57. This is an interesting one. 3x minus 4, 3x plus 4. So notice these polynomials are the same, except one's got a plus here and the other's got a minus. And something interesting happens in that case. 3x times 3x, 9x squared. Minus 4 times 3x is minus 12x. 3x times plus 4 is plus 12x. Minus 4 times plus 4 is minus 16. So the minus 12x and the positive 12x, right, they add to 0. So we often say they cancel additively. So we kind of, as a method of sort of record keeping, you do that to kind of help yourself along if you have a lot of such cancellations. So this becomes 9x squared minus 16. So more generally, this is a formula to remember. In general, a plus b times a minus b, so this is an example of that, is going to be a squared minus ab plus ab minus b squared. And then these go away, and you have a squared minus b squared. Okay, so that's a standard thing that pops up every so often. It's often called the difference of two perfect squares, this formula. Difference of two perfect squares. A lot of examples will use that because it's an easy polynomial expression to deal with. 5763. It's 63 more the same. Well, that's y plus 2 to the third. Let's leave that out for now. 63, 69. So this is a 3-term times a 2-term expression. So something like number 70. Yeah, so 69, a lot like 70. So 2x minus 5 times x squared minus x plus 1. Alright, so 2x times x squared. So every term in the first times every term in the second. So let's write it out fully. Not because I want you to write it out in as much detail, but just in case. Just in case you would like to see the detail at this point. What I was mentioning yesterday, right, 2 terms here, 3 terms there, so 6 terms altogether. 2x times x squared, 2x times minus 1, 2x times 1, minus 5 times x squared, minus 5 times x, minus 5 times 1. As I was saying yesterday, only show as much work as you need to show for you to feel comfortable you got it right. Don't show more than that. It's just clutter. Only use what you feel you need. Minus 5x times minus x. The minuses cancel when you multiply them together, right? It's just plus 5x. And then minus 5. Okay. So I have minus 2x. Well, let's do the highest power is x to the third. So I got 2x to the third, no other x to the thirds. Then x squared minus 5x squared right there. Right. And then x. So I have minus 2 plus 2 and 5. Leaves me altogether 5x. And then minus 5. Okay. And then like 74, dealing with some rational exponents. It's no different than the integer exponents. All these, the 78 has got rational exponents. 74 does too. It's no different than integer exponents. So 74 is x to the fourth, 2x to the 3 4, no, not x to the fourth, x to the 3 halves, no, x to the 1/4, 2x to the 3/4 minus x to the 1/4. Multiply, the x to the 1/4 by both terms, and this, and again here you have x to a power, x to the power. When they multiply together, you add the exponents. So it's 2x to the, 3/4 plus 1/4 is just 1. Plus x to the 1/4 times minus x to the 1/4. Add the 1/4 and the 1/4. You get 1/2. And then, of course, it's a minus, not a plus. So x to the 1/2, which you could also write as 2x minus square root x. But, this expression is nice. This one is fine, too. That's an acceptable answer. Okay, so rational exponents, just the same as integer exponents. Just be careful when you're adding fractions together because it's easier to make a mistake. All right, so those are the problems. If you haven't done them on your own, you can do these on your own now, and check your work against mine. You've got all the calculations done here. So you can do them on your own, and then check your work against mine. If you get something wrong, then try to fix your error. All right. And again, only show as much work as you need to feel comfortable you're doing the problem right. Don't show more work than you think than what you need. It's not the right way of doing things. I don't know why they always say show all your work all the time. Maybe when you're dealing with high school kids, it's different, but if you're gonna write to somebody, let me just ask you a question, just in generality. If you're gonna write a message to somebody, about something, what, just some information, what, that you want to announce to somebody. How should your letter be? How should your message be? Should it be long? Should it be long and discuss every detail? Or, should it be brief? Put in as much detail as is necessary, in your message, but be brief. Get to the point. Say what you want to say. Get to the point. Don't go on and on and on about things that are peripheral to the issue at hand. And when people say, write out everything, that's what that means, right? Go on and on about details that are not important. Okay, don't write out everything. Write what you need to get it right. Okay, I don't need to see more work. And if, by chance, not that anyone in this class would, but if by chance someone happened to cheat, I would know it just by seeing what they wrote because they didn't write anything, right? Or they didn't write a step that would have been necessary to do the problem. Like even I wouldn't be able to skip that step. All right, anyway, so P6. Factoring. So a polynomial in standard form, okay, is a sum of monomials. Polynomial or rational expression. In standard form is a sum of monomials. So, for example, 3x squared minus 10x to the 1/2 plus 1. I'm just going to use a polynomial. 3x to the third plus 10x minus 1. Something like that. Okay? So a sum of monomials. Right? The order of operations one, exponentiation. 2, multiplication and division if there is any. 3, addition. So the final operation is addition and subtraction. Okay, if you were to evaluate this expression, like if I was to say x is 2, if x is equal to 2, first I have to evaluate the exponent. Then I have to evaluate the multiplication. Then I evaluate the addition. 24 minus 20 is 4 plus 1 is 5. Okay? So in standard form, the final operation is addition and subtraction. The final operation is addition and subtraction. In factored form, the final operation is multiplication and exponentiation. Are multiplication, division, and exponentiation. Exponentiation is essentially multiplication anyway, but right. So addition is not the last operation. That's the point. So for example, 3x plus 1, x squared minus 4, something like that. Okay. Squared. Put it up here. Okay. The final operations here are multiplication and exponentiation. This multiplication here and this exponentiation there. All right. There is addition and subtraction, but they're inside these parenthetical expressions. Inside the parenthetical expressions. And once you have things in factored form, you can do different things with them that you can't do when they're in standard form, and vice versa. So sometimes standard form is appropriate, sometimes factored form is appropriate. Okay? So, for example, also factoring quadratics. So probably you've done this sort of thing already, but it stands to review it. So a polynomial is quadratic. So quad is 4, so it's kind of annoying that 4 goes with this. If it is of the form ax squared plus bx plus c. By the way, this is a polynomial. It's a polynomial expression, if you will. It's not an equation. There's no equation on the page yet. We haven't done any of those yet. It's important to know the difference. So a polynomial is quadratic if it is of the form ax squared plus bx plus c. So the only powers of x are x squared, x to the first, x to the 0. Okay, and sometimes they can be factored nicely, not always. A quadratic polynomial can be factored into a product of two what are known as linear polynomials. So linear means the only powers of x are x to the first and x to the 0. So sometimes you can do that, not always. So x can sometimes be written as, say, like p1x plus p2, q1x plus q2. So the question is, what are p1 and p2 and q1 and q2 if they exist? And you can't always do it. Okay, sometimes you can, sometimes you can't, and we will go over situations in which that sort of thing can happen. Okay, so the best way to go about doing this is really just to run through some examples. So, some nice examples here. Oh, well, let me say this before I do these examples. Okay, so when it does factor, okay, p1x plus p2 times q1x plus q2. When you multiply that whole thing together, right, expanding into standard form, going back the other way, unfactoring, if you will, this becomes p1 q1 x squared plus p1 q2 plus p2 q1 plus p2 q2. So this final number and the first number are the ones really to look at, right? So this should be equal to C, and this should be equal to A, and this one is a little bit harder to put your finger on, but when you find out the possibilities for A and C, then you see which one, if any, works out here. So, for example, x squared plus 7x plus 12. All right. Well, this is a 1. The coefficient here is a 1. And in terms of integers, 1 is 1 times 1. And 12, well, it's 4 times 3. It's also 12 times 1. It's also 6 times 2. Right? Those are different ways to write 12 as a product of two numbers. Okay, well, let's look at one of them, 3 and 4. Notice that 3 plus 4 is 7, right? So that might work out here. 3 plus 4 is 7. So x plus 3, x plus 4. And the question is, does this work? Okay, does this work? So before we say it's equal, let's check it. Okay, let's check it and see what it is. X plus 3 times x plus 4. Well, it's first, outside, inside, last. So that's x squared plus 4x plus 3x is 7x plus 12. So that works out. So x plus 3, x plus 4. So that one did work. Notice that x plus 6 and x plus 2 won't work. Oops. X plus 6 times x plus 2, that won't work. If you were to multiply this together, it would become x squared plus 6x plus 8x plus 12. So that's x, or not 8, but 2. 6x plus 2x plus 12. So that's x squared plus 8x plus 12, right? So that didn't work. Nor does the x plus 12, x plus 1. That's not going to work either. That's x squared plus 12x plus x plus 12. So that's x squared plus 13x plus 12. So that didn't work. All right, so in front of the x squared is 1, in front of and then the constant term is 12. 12 you can think of as 12 times 1, 6 times 2, or 3 times 4. And then you can try the different possibilities and see which one works. Well, here we see that x plus 3 times x plus 4 multiplied together does equal the polynomial we're looking at. So now this polynomial is in factored form. The final operation here is multiplication. There is addition, but that has to happen before the multiplication inside these parenthetical expressions. How about this? So examples, x squared minus 7x plus 12. The only difference in here between this polynomial and that polynomial, okay, is that this is a plus 7x and this is a minus 7x. And 12, of course, is also equal to not just 4 times, positive 12 is not just equal to 4 times 3. It's also equal to minus 4 times minus 3. It's also equal to minus 12 times minus 1. It's also equal to minus 6 times minus 2. And then if you run through these possibilities again, with these negative numbers, x minus 3 minus 4, all it does is it changes the 4x and the 3x to minus 4x and minus 3x. So you get minus 7x. And here, you get the same outcome. Right? It's x squared minus 6x minus 2x plus 12. Minus 6 times minus 2 is plus 12. Right? So we have x squared minus 8x plus 12. Same thing with this. Right? So we see that this is x minus 3 times x minus 4. And that now is in a factored form. It's a factored form because the final operation there is multiplication. There is addition, subtraction happening inside those parentheses, but you know, those come before the multiplication, which is the final operation here. So here's one thing to notice that from these two examples. Right, so x squared minus bx plus c, right, implies, so if it factors, so if x squared minus bx plus c factors, okay, then you know, as x minus p, x minus q, it will look like x minus p, x minus q. where P times Q is C. Similarly, if you've got where P times Q is equal to C and P plus Q is equal to B. If instead there's a plus here, x squared plus bx plus c, then it's going to be x plus p, x plus q, where p times q is equal to c and p plus q is equal to b. All right, so if your c is positive there, if it's x squared minus bx plus c, then you factor like this, x minus p, x minus q. If it factors, it might not. If you have x squared plus bx plus c, then it's going to factor as x plus p, x plus q, if it factors. So, a couple more examples. So how about x squared plus 6x plus 9, right? Well, 9 is equal to 3 times 3. And 6 is equal to 3 plus 3. So, right, so the final answer here is going to be x plus 3 times x plus 3, which is also x plus 3 squared. So either of these is an acceptable final answer. This one is better, but either one is fine. 9 is equal to 3 times 3, and 6 is equal to 3 plus 3. Similarly, if you had x squared minus 6x plus 9, this is going to be x minus 3 times x minus 3, which is x minus 3 squared. Both of these are in factored form because the final operation is multiplication or exponentiation. Right? 9 is 3 times 3, 6 is 3 plus 3. Because this is positive and this is negative, you have these two different factorizations, x plus 3, and x minus 3, x minus 3. Not that you have to have the same identical linear polynomials there, but you could also have, different ones like in the previous example. Let's take one more. X squared plus 5x plus 6. Right? Well, 6 is equal to 2 times 3. Well, let's do a little different. How about 7? 6 is equal to 6 times 1. 7 is equal to 6 plus 1. All right, so this one is going to factor as x squared plus 6, x plus 6 times x plus 1. All right, 6 is equal to 6 times 1, and 7 is equal to 6 plus 1. So we've got this factorization. Similarly, if you had x squared minus 7x plus 6, then they have to be negatives, x minus 6, x minus 1. All right? So that's the case when the constant term, the x to the 0 term, is positive. If the x to the 0 term is negative, so I'm sorry, if how should we say it? X squared plus or minus bx, and then minus c. So this is positive, this is minus, this is negative, whatever it might be. If it factors as x, if it factors, then it will look like x plus p x minus q, where p times q is equal to c, and p minus q is equal to plus or minus b, or whatever the case might be, right? If it's a positive b or a negative b. So for example, here, x squared minus x minus 12. Right? X squared minus x minus 12. Well, 12 is equal to 3 times 4. Right? And 12 is equal to 6 times 2. And 12 is equal to 12 times 1. If you're just working with integer factorizations. Okay, but since it's a negative 12, it's got to be x, negative 12 is equal to, so let me write it this way, minus 3 times 4. It's also equal to positive 3 times minus 4. Minus 12 is minus 6 times 2, which is equal to also positive 6 times negative 2. And negative 12 is equal to negative 12 times 1, or 12 times negative 1. All right, so we have all these different factorizations to, these factorizations of negative 12 to contend with here, right? So the possible answers are going to be x minus 3, x plus 4, possible answers.
Will there always be a factorization pair that works out? Or will there
No, absolutely not. Yeah, absolutely not. There will not always be. I won't ask you to factor something that doesn't factor, but in general, some problems can come up where they don't. It doesn't factor. All right, so x plus 3, x minus 3, x plus 4, x plus 3 minus 4, x plus 6, x plus 2, x minus 6, x minus 2, x plus 6, x minus 12, x plus 1, x plus 12, x minus 1. Okay, so we've got 1, 2, 3, 4, 5, 6. We've got these 6 possibilities here. Well, which one is it? Right? Which one's it going to be? Well, it's got to be this one. No, it's not got to be this one. It's got to be this one. Because 3 minus 4 is negative 1. Right? 3 minus 4 is negative 1. And 3 times negative 4 is negative 12. So that's the factorization. X plus 3, x minus 4. Let's check it out. Let's check. X plus 3 times x minus 4. Well, x times x first is x squared. 3 times x minus 4 times x. And then plus 3 times minus 4 is minus 12. So I have x squared plus 3x minus 4x. Right, that's minus x minus 12. And that's what we're looking for. Similarly, x squared plus x minus 12. right? X squared plus x minus 12 is going to be the x minus 3 times x plus 4. Right? Because minus 3 times 4 is minus 12, and minus 3 plus 4 is positive 1, and that's the coefficient on the x. And then all these other products, you know, well, other examples. So x plus 6, x minus 2, that's going to be x squared plus 4. I'm sorry, I should be going the other way. X squared plus 4x minus 12, that's x plus 6, x minus 2. X squared minus 4x minus 12, that's going to be x minus 6x plus 2. Because minus 6 plus 2 is 4. And then 6 minus 2, or minus 6 plus 2 is negative 4, and 6 minus 2 is positive 4. However, something like this, x squared plus 9x minus 12 does not factor using integers. Because no factorization of 12, right? Well, even we'll make it a positive. Because a times b equal to 12 never satisfies a plus b equal to 9. So right then and there, you've automatically got a polynomial that does not factor, quadratic polynomial. A polynomial of the form x squared plus, x squared plus some power, power of x squared, x to the 2, x to the 1, x to the 0. So any number that you put here, so I mean, how many factorizations of there are of 12 using integers? It's just 12 times 1, 3 times 4, and 6 times 2. So, I mean, that gives you a very limited set of numbers you can put here where you actually get a factorization, right? Just a finite, 6 or 7, different numbers that you could put here. At most 6. Right, using those factorizations of 12. Any other number you put, you're not going to factor. So to answer your question, do polynomials always factor? And the answer is no. As a matter of fact, they usually don't. But, we have to learn to deal with those that do. Okay, so we do a lot of practice with those that do factor. Okay, so that's all for today. So we're going to need to do a little bit more talking about things in this section. So we'll continue that tomorrow, okay? So have a good day, everybody, and we'll see you tomorrow. Email me with any questions or concerns, okay?
Thanks, sir. Have a great day.
You too.